And welcome back to another LeetCode problem. We're continuing our journey through the advanced graph problems. And next on the list is minimum cost to connect all points in a grid. So this is a LeetCode medium problem. And in this scenario, we're giving a bunch of points in a two-dimensional coordinate plane. And we basically need to find, we need to connect them to a tree so that the total sum of the distances is minimal. But let's read through this first. So we're given an area of points representing integer coordinates of some points on a 2D plane. The points at position I equals a x and a y coordinate. The cost of connecting 2 points x and y with other 2 points x and y, with 2 points and the first point being xi, yi and the second point being xj, yj, is the Manhattan distance between them. So the Manhattan distance is just the absolute value of the difference of the x values plus the absolute difference between the y values. Val denotes the absolute value of val. Okay, cool. Return the minimum cost to make all points connected. All points are connected if there is exactly one simple path between any 2 points. Now, the sharp observer will notice that this is a minimum spanning tree problem, and there are a couple of algorithms to solve that. There's Kruskal's algorithm, there's Prim's algorithm, and I believe Prim's algorithm is going to be the optimal choice here, which will give us O of n squared time and O of n space complexity. Now, Prim's algorithm works by, well, you just pick one point, and then you start to pick the edge that has the lowest cost associated with it to get there. So if we look at this example, you can see that it connected all of the shortest edges between points. Did not pick the edge from here to here, did not pick the edge from, here to here. It picked all of the smallest edges. And that's exactly what we're going to do, but we're not going to get around two nested for loops where we compute every distance to every neighbor of a given point. However, once we've reached a node, we know that we will never have to compute another path to that node again. So we will take advantage of that with a hash set where we keep track of all the nodes that we have already connected. So, well, what are we going to need for this? Well, we're going to need a visited set. And we're going to start with a node, and we also need a result value. So 0, because the result value is what does it say? Return the minimum cost to make all points connected. So it's just the sums of all the cost edges between all the nodes, and the cost was the Manhattan distance between them. So that is what we need. We also need a way to keep track with, how many edges did we create, right? So we're given a list of points, and should probably keep track of how many edges we have. Edges, and all of that is going to be 0 in the beginning. And now we'll continue in our loop until we connected all of the nodes. So while edges smaller is length points, right? Or we could also just use visited instead, while length of visited is smaller than length of points. So maybe we don't even need this edges variable here. Cool. Next, well, we're starting at node 0. We can start at any node because we're going to have to compute a connection to node 0 anyways. And so the node values, they don't say what the nodes are labeled, what the value for I and j are. So we're just going to assume that they're 0 index, and we start with first node, and we label it node number 0, which is in the points array at index 0. Okay, so we're going to add that node to our visited set. Now we don't know what the next node is yet, so I'm just gonna label it -1 for now. Now what we'll do is we will iterate over all of the neighboring nodes. And right now, all the neighboring nodes is every node. All of them are candidates for the next neighbor. So for dest in range length points, right? Well, if the destination is visited, well, we're not going to compute another path to that node. And visited, just going to continue to ignore that. Otherwise, well, what do we do then? Well, we have to compute the distance between the source and the destination. So distance is going to be, well, the absolute difference between the points x and the points y values. Points, destination, and 0 for x, minus points x coordinate of the source value. That's one thing. And we're going to add the same for the y coordinate. So that is the distance that that we have to compute. And now we have to check whether, well, we now have to kind of find the destination node that has the smallest distance. So what we'll do is, how should we do this? We could use, what could we do? Well, we can compute, if we keep track of the distances to that node, well, we have to keep track of, what was the distance to reach a certain node. So what's the path sum? So if we start here at the edge, then we go to this node at cost 4. And then we go to that node at cost 3 would be 7. And then this node also cost 4, right? So that is one way to reach it, but we could also just go from here to here. So how do we ensure, we pick the shortest one? Well, we always pick the shortest edge, right? That is how we do that. But we now need to compute, well, the minimum value between the distance, minimum value of the distance to reach that node, or node infinity if we did not reach that node before in any shorter distance. So we have to compute that between that distance and the distance. Now, this at is t equals that. So that is, we're updating the distance to reach the node, and we probably need to have a dictionary for that as well, for these distances. So we update the distance to reach the destination node with either the current value to reach that node or the new distance value, because we're going from source to destination over the distance of so. Right, now, well, we have to check one of two things. Well, if we have not picked a next node, we have to assign it. So if next source equals -1, meaning we haven't initialized it, then, well, we're going to have to set it to the destination node. And the other case when we have to do that is when the distance value to reach this is smaller than the distance value to reach the next source node, so the previous one that we picked. So this ensures that next source will point at the destination node that is in the closest proximity to the source node. And we keep track of the distances to the destination node from the source node in our little dist dictionary. So basically, every time we consider going from one node to another node, we always update. How do you say? The distance it takes to reach that node. Right? So yes, that's basically what we do. Cool. So, well, and this will go on until we've visited all of the nodes in the grid, right? And we've constructed all of the edges that way. And of course, we are not really remembering the edges, we're just remembering the cost, right? So, and after we've explored all the neighbors of the source node, what do? Well, we have to add the distance to our result. That is the distance from our source node to the picked next destination node, right? And that would be this. Now, our visited set has increased already. And could also put that here if you wanted to. Doesn't really matter. But our visited set has increased already. But we now have to say the source node is the next source node. So that's what we have to do. And yeah, and then at the very end, we just return the result. Return the result. Now, in terms of space and time complexity, I said in the beginning that we're going to deal with O of n squared time. And that is simply because we have two nested loops, and both of them go over the entire range of our points array. Time and O of n space, because we're only going to need space for storing the points or the distances to those points. So if we run this now, let's see what happens. We have a typo somewhere, an unmatched clothing parentheses, or parentheses, and next source, this next source. Key error -1, next source. Let me see, destination. Next source is DST. Oh. Yeah, so we have to, this order needs to be reversed, otherwise we're updating it too early. We just computed the new distance to the next source, and only after we add that to the result can we assign the next source for the next iteration of the while loop. Key error -1. Next source. Here we set next source, that is correct. Here we compare that to -1. And here do we set that to -1. Let me think. Right. Maybe this is not working as intended. We're adding 1. Can I see the error? Let's see. I think so. We're creating our distance dictionary or visited set. We are initializing source and the result was 0. And oh, there is an off by 1 error here, right? Because the number of points and the number of nodes that we visit. So the last node that we add, we will not have any edge from that node. Right. Yeah, that's the thing. So we submit this again. Ta-da, it works. So yeah, so if you want to review this, I would suggest to have a look at Prim's algorithm. That would explain exactly how that works. And there are other solutions like Kruskal's algorithm, or you can, I mean, Prim's algorithm in this case is really just a brute force, isn't it? And it's a greedy as well because it picks the next closest point to the tree structure that we already established. All right, that's it for this little video. Let's check off this from the list. And swim in rising water, I believe. Not sure if we did this one. Well, we will look at it in the next video.